Hello, I am Banyat Pat, and for the purpose of this video, I will be explaining quantum entanglement to you guys so that we can use this knowledge to prove why faster than light communication is hypothetical. Quantum entanglement is where a system of particles act as one single entity, in which any changes in one single particle will simultaneously affect the other. Let's say I have a coin. If I flip a coin, I will either get a head or a tail. But what if I didn't flip the coin? Can you guess what I can get? Well, I can definitely get a head and a tail, but I don't know what I will get until I flip the coin. When a particle is said to be in superposition, that means that the particles can exist in all of its possible state at once, in which the particle can be both spin up or spin down. Why is it so? Because we're uncertain of its exact state until we measure it. Particles have spin. This spin can be thought of as the spin of the Earth on its axis or a spinning top. It isn't actually rotation in physical space. Particles have spin up and spin down. For an entangled pair of particles, the spins are always paired. Let's say that we measured two entangled particles that were separated light years away. Both particle A and B are in a superposition of the state of both spin up or spin down. If we measure spin up for particle A, particle B will have a spin down. We can keep doing this forever and still get 100% correlation. Why is it that the correlation is always 100%? This is because particles are connected together and are communicating to each other so that when you measure one particle to have spin up, that particle tells the other about its spin, so that it changes to spin down in order for the states to always be correlated. This behavior is called spooky action at a distance. Even though this may sound very nonsensical as you would break the universal speed limit, the speed of light, experiments have proven that spooky action at a distance does indeed exist, based on how particles violate a set of inequalities called the Bell inequalities. So does this mean that faster than light communication is possible? In up to 5 more years, the first manned mission to Mars will be underway. Assuming that radio communication will be used for this mission, a radio wave takes about 13 minutes to reach a spacecraft near Mars and 13 minutes to come back. If anything goes wrong with the spaceship, you won't know until 26 minutes later. That 26 minutes will cost human lives. What if we have a Morse code in which we can change the state of the entangled particles for instant communication? Well, that sounds like a great idea. So why doesn't the rest of the world use communication technologies like this instead? This is because it is impossible to manipulate the particles to communicate with each other, as when the particles are not being measured, you can't know what state they're in, because they're in the superposition of all of its possible states. But this makes sense, right? Let's say I have a deck of cards behind my back, and I told you to guess, what card will I get next? You wouldn't know what card I would get next, unless you come to look behind my back. And you can't tell me to pull out a king of diamonds, because I don't know what card I have behind my back. And that's the same with a particle. Particle doesn't know what state it's in until you measure it. Oh, I got king of diamonds. Let's say you didn't measure the particle spin state. If you did, then the superposition of both particles will collapse simultaneously to reveal only one observed spin for one particle, and by default, the other. If you did change the state of one particle, it wouldn't affect the other anymore. So the problem arises. You are not transmitting information, but rather you're just revealing information. For this example, I have two boxes. One box has a red card and the other has a black card. Let's assume that the red card is spin up and black card is spin down. Let's say you measure the state of two entangled particles with another group at another location. So you have one particle and the other group has the other. And you've agreed that you're going to measure the particle spin state. Well, let's measure this. I got spin down. The other team doesn't know whether or not you have measured the particle spin state because they haven't measured the particle spin state yet. Therefore, you need to send them a message that is limited to the speed of light, because information is still not accessible to them unless they measure it. This is what makes faster than light communication hypothetical at the meantime. Hey, did the other group measure the particle spin state yet?
No.
However, this doesn't mean that quantum entanglement is useless. The theory actually allows us to visualize and create more complex technologies, such as quantum computers. It is now being developed as it offers several advantages over classical computers in handling certain sets of enormous calculation. So, on the good side, quantum entanglement is a significant theory of modern physics that will have a major impact on how we create technologies of tomorrow.